Let us recall what we did last time. So last time we kind of talked about details of Landau-Ginzburg theory. So in particular, we talked in details about contact terms, to be more precise, ambiguities in a contact term definition. And we kind of verified that despite of having ambiguities in the contact terms, we still have well-defined Landau-Ginzburg-Saito recursion for correlation function. So we can show correctness recursion. And after we discussed correctness of recursion, we kind of briefly talked about symmetry of 4 and higher point functions. In Landau-Ginzburg theory, and from this kind of symmetry properties, I kind of argued and provided some kind of proof in a 4-point case, some kind of result, known result in a 5-point case, and conjecture for n-point case. So let's call it, like we talked about, Wood-Jackson conjecture. So that given certain properties, this Wood section map, which maps Jacobi ring into kind of holomorphic functions by gradient ideal that given a certain specific assumptions about this good section, the all endpoint correlation functions will be symmetric, and this section, kind of this conjecture was inspired by Koji-Saito theory of primitive forms. So kind of all this discussion was meant to illustrate that like the kind of word S in this one side of theory is kind of very important. Here, like this letter S stands for Koji-Saito, and that is something that mostly missed, especially in the physics literature. So people just kind of saying that for a mirror of toric variety, we got a Landau-Ginzburg theory with a certain mirror superpotential, and then we can just use this mirror superpotential to evaluate everything using some kind of residue form. However, that's kind of not entirely correct, and kind of as a key step is you need to use some complicated change of variables to get an actual match with chromophyton invariance. And this complicated change of variables is essentially encountered in this kind of good section definition and good section choice. So that's why kind of in our proof of a mirror symmetry using tropical geometry, so this kind of immediate implication that in tropical mirror symmetry proof, so we kind of expect, or we need to see how the good section mirror and in the later lectures we will see kind of how to give a description of a good section and how to extract it from kind of data on A models. So starting from today's lecture, we will kind of gradually get into our next subject. So we discussed, like in previous group of lectures, we discussed like A side of a mirror relation. So then we discussed B side of a mirror relation, Landau-Ginzburg side of theory. And starting from today's lecture, we will kind of in details talk about kind of mirror map. How to make chromophyton invariance on some toric variety X into Landau-Ginzburg side of theory on here the target space for Landau-Ginzburg side of theory is very easy. So it's n-dimensional algebraic torus where m is the complex dimensions of X. So this part is kind of extremely easy. So then, okay, holomorphic top form is also canonical on this space. And the kind of interesting kind of the part of Landau-Ginzburg side of data that interesting depends on X is this mirror superpotential and kind of mirror version of a good section, which I will call tropical good section, because so far we only know how to get it in kind of tropical geometry. And we kind of want to construct this mirror map. But before we even start, we need to kind of give some kind of good description or some explicit description for toric variety, because to study like holomorphic maps or to study holomorphic curves or tropical curves in a given toric variety, we need to have like some nice kind of preferably combinatorial structure of a toric variety. So what we want combinatorial description with a formal definition. So to give some nice description, we need to recall the definition of a variety. So kind of definition. So if variety X is variety in the sense that it is like zero locus of some algebraic equations with actions of algebraic torus. So that's kind of where name Pori comes. So it's variety with this additional structure that there is an action of algebraic torus. So algebraic torus is essentially some copies of C star. And in this action, we kind of require that it is not trivial in a sense that the variety X itself, as a kind of open set, it contains algebraic torus of dimension n, where n is a complex dimension of X. So that is kind of formal definition. Okay, so let me give you some examples. Okay, even for example, let me specify kind of what we mean by action of algebraic torus. Here we mean necessarily multiplicative action. So for algebraic torus, okay, let me do one-dimensional version. So C star is essentially what? Is a complex numbers where I remove zeros. So it's non-zero complex number. So if I have non-zero complex number Z, or okay, for algebraic torus, so elements from here, if I have like T1 and T2, that are two non-zero complex numbers. So then there is kind of multiplication of this non-zero complex number, and that is again non-zero complex. So multiplying two non-zero complex numbers give me non-zero complex. So I have this multiplication operation, and then because the complex number is not zero, so for a complex number T1, I can construct its inverse. And that acts as kind of inverse element for this multiplication. And there is a special non-zero complex number 1, such that if I multiply any t by 1, I get t. So hence here I have a multiplicative group. So kind of commutative associative multiplication with inverse. And this kind of multiplication structure, it kind of naturally defines an action of algebraic torus on itself. So here we just say an element Z, and kind of if we choose element T here, then the action of this element on the whole algebraic torus is just multiplication of Z by T. And here, when we say algebraic variety kind of endowed with this multiplicative action, we really mean that that kind of in some local coordinate, this action is just multiplication by T. Okay, so first example of kind of storage variety is kind of algebraic torus itself. So by definition, it has an action on itself. However, this term is kind of non-compact, so it has kind of C without zero, and C itself is non-compact, and removing zero doesn't make it one. So this kind of trivial example is that we can take kind of C itself, which is C star, and we added kind of 0 point. So what is the action of torus? So we have kind of coordinates on this space, so they are just complex number Z, and the action of the torus, we just multiply this complex number Z by T. So here what we see, so C star, okay, so it contains complex numbers contain C star with an open set, and the action on C star is a standard multiplicative action. While 0 itself, it has this nice property that if I take 0 and multiply it by any complex number, or in particular by any non-zero complex number, I still get 0. So in this sense, 0 is also a kind of special orbit of this fifth direction, and this orbit that consists of single point that kind of doesn't change. So the next example also of a toric variety in one complex dimension is one-dimensional complex projective space CP1, which is essentially C and the at kind of point of infinity. So in this case, kind of to carefully see that it is a toric variety, so we can do the following thing. So here we can introduce kind of two coordinate patches. So we can cover CP1 by two coordinate patches like say CC and then CW with a transition function W1 over Z. So then on the coordinate patch CV, so on CV, we kind of introduce multiplicative factor into Z times T. So the same as in kind of in the complex numbers. So then what happens to this multiplicative action if we kind of take some points in CV that are also points on CW, points that lie on intersection T. So W is one of Z, and under this multiplicative action, so W would go to W multiplied by 1 over T. So in kind of W coordinates, we still have a multiplicative action because 1 over T is also element of a torus. So in both patches we have multiplicative action, and this multiplicative action is kind of compatible with this kind of transformation of coordinates between CV and CW. So that makes CP1 also a toric variety. So it's essentially like C star, which is kind of open set inside of CP1. And then we added 2 points. We inserted back a 0, which we removed to get from complex numbers to get C star, and we added point at infinity. Okay, so let me give one more example, which is kind of less trivial. So let me look. Yeah, let me look at kind of some singular case. Let me look at a complex curve in 2 dimensions, which is singular complex curve. So it is 0 locus of the equation x cubed minus y squared. So here x and y, they're just complex numbers. So that is some kind of normal curve like this. And this kind of model curve is a toric variety, because here what we can do, we can kind of remove a point from this curve. So this curve contains point 0, 0, which is point. And that curve. Okay, so here we can solve this equation parameterized form. So we can say that x of lambda is lambda squared, and x and y of lambda is lambda cubed. So that is parameterized form for this curve. And if you remove 0 point, so then it's the same as kind of removing, so this thing same as removing lambda equal same as lambda equals non-zero, so we remove just lambda equals 0 from parameterization, and then this thing is kind of isomorphic to algebraic topos. Space of parameters lambda that can take non-zero complex number. So then on this kind of parameterized version of a curve, so if we remove 0, we can see that there is a kind of standard multiplicative faction. So if I kind of change my lambda into lambda times e, so e is a complex number, we see that the value of lambda times t and x of lambda times t is also solution to this equation. So here y of lambda t lambda t cubed and x of lambda t lambda square t square. So we plug it back and see that it's also kind of some point on this curve. So hence there is an action of C star that takes like a point away from this orange point on the curve and moves it to some other point. So the action roughly takes a point here and moves it to some other point E that you get after T. Okay, and then we can put this point back as kind of trivial orbit of this torus, and that will make C into a toric variety, and it's toric variety of dimension 1. So it's single equation into vector. Okay, so that was kind of simple examples of toric variety that we kind of constructed using the standard definition. So this standard definition is kind of okay. So it defines the toric variety, but checking toric varieties like case by case that takes some effort, and if you go to high dimensional cases, that is not very practical. So therefore, we need some kind of better way of getting maybe not all toric varieties, but at least some families of toric varieties that we can work with. And let us recall that among our examples, we have this particular example of the CP1, and then CP1 is kind of has very standard interpretation as a quotient space where we take the two-dimensional complex plane. So on C2, we have actually two copies of C star action. So C2 is like two copies of C, and on each copy of C we have a torus action. So it means that if we have a pair of coordinates Z1 and Z2 on C2, I can kind of independently multiply them by T1 and T2, and that's just C2 action. So CP1 is kind of can be constructed from C2 if you remove 0 and quotient by kind of diagonal C star action. So diagonal action means that we choose a kind of subgroup like C star subgroup inside of C star square such that T1 equals T2. So that is kind of meaning of this diagonal action. So CP1 can be obtained from some kind of toric variety in higher dimension and by taking quotient of a torus action. So this construction looks kind of promising because sort of the data of this construction is essentially some kind of standard space like C star to some power quotient by an action of C star or algebraic torus, and yeah. One example. Motivates consider some quotients. So to consider quotients which are roughly c to some power minus some subsets, and then quotient by c star to the power. So usually these subsets, they are kind of some orbits of a lower dimension of this C star. Lower dimension orbits. And it turns out that is well-studied construction, so that is known as GIT quotient. So GIT stands for geometric invariant theory. However, okay, so GIT quotient is kind of nice, but we can make it even nicer. So it turns out that C star itself. Okay, let me take one copy of C star. So it is non-compact group. So it has kind of non-compact subgroup R and kind of compact part S1. So here, okay, in this translation, we can say that any complex number is essentially a product of a magnitude that I will denote as e to the r. So magnitude kind of runs from 0 to infinity, which I can exponential parameterization. I can parameterize my real number r, and the phase I phi phase on S1. And it turns out, because we kind of doing this quotient in algebraic geometry or equivalently in holomorphic setting, then the action of kind of radial part, non-compact part, and this angular part, they are related to each other. So we say that the action of C star is some kind of multiplication by t. So therefore we change a phase kind of by the same amount as we change radial coordinate. So we shift like phase by a phase of t and radial part by this magnitude of t. So it turns out that, okay, so there is a theorem that under some good conditions, which are satisfied when this group action, or when this group is abelian, that this GIT quotient is actually isomorphic to symplectic quotient. So the symplectic quotient is denoted like this. So it's on the quotient of this also space Cn plus S over a kind of compact real group, which is a compact subgroup of this C star to the power S, which is just U1, okay, S1 is the same as the Lie group U1, so U1 to the power S. So here, to define the symplectic quotient, I need to, so this notation here, that means it's symplectic quotient at level mu of the momentum. And it turns out for kind of our various computations and various explicit formulas, it will be more efficient working with symplectic quotients. So therefore, I will kind of rely on the theorem that there is a relation between symplectic quotient and GIT quotient, and I will kind of explain how to get this subtraction of lower dimensional orbits. But mostly we will kind of work with this presentation for toric variety. But to use this presentation, I need to give you a formal definition of how to construct this new object, which is this double line. Okay, so once again, let us start from the beginning. So let us kind of C to the power n plus s is some kind of copies of or Cartesian product of C complex numbers. So C is a symplectic manifold. So in particular, if I use, okay, so there are like several ways of seeing this. So the simplest way is to observe that C is isomorphic to R2, which is a cotangent bundle to R. And that kind of cotangent bundle to anything is a symplectic manifold with some kind of canonical symplectic form, which is kind of with exact canonical symplectic form, which is D of PDQ. Or we can do it in more specifically, so we introduce complex coordinates, Z and Z bar, and then just by hand introduce a symplectic form, which is Y dV over dV bar. And we can see that this form is a closed form. And the second property is that the symplectic form should be invertible, and indeed this symplectic form is invertible. Or, okay, so the necessary condition for invertibility is non-degenerate. So it means that if I compute it on pair of vectors, pair non-zero vectors, I will get non-zero. So it's non-degenerate, it's invertible. And these two conditions, omega two forms on phi, so two form which is closed and non-degenerate and invertible, defines me a symplectic structure on C, and that makes a pair C and omega into symplectic manifolds. And this symplectic is kind of the same as this word symplectic in symplectic motion. So now, if I have symplectic manifold, or let's say M omega symplectic manifold, so here not necessary complex. So real symplectic manifold for two. So symplectic manifold and let G be kind of single. So then we can consider action of G on M. G on this. Okay, let's like look action of G on M. So that is essentially a map of the following type. So for every kind of element G and G, so we have a map. Let's call it phi G. That is takes M to M, and then we demand that this diffeomorphism of M. So this map is kind of smooth and inverted. So that kind of one condition, and then second condition, if we have kind of G1 and G2, so we want this map to be compatible with group multiplication. So in particular, we want phi of G1, phi of G2, okay, phi of G1 times G2 to be phi of G1 composed yeah, I think it's composed in this way. So we want, like for every element of G, we want to have a diffeomorphism of M, and then for pair of element G1 and G2, we want a multiplication of kind of group elements to lead to a multiplication or to lead to a composition of the corresponding. So given this kind of collection of maps phi G, with the property, we get a group action of G on M. So now our manifold M, it comes with additional structure, which is the symplectic form. So and kind of given this map phi G M to M, so this map it defines a pullback map that takes kind of differential forms of M and makes them into differential forms. So therefore, we can ask the following question. So what would happen if you take a pullback map of our symplectic fork omega? So if we impose this condition that omega is invariant on the pullback map, then the action that we call the action G omega simplex. So it preserves a structure, symplectic structure on. Okay, so we introduced the notion of symplectic action. Well, now let me see. Next. Okay, so then for symplectic action, okay, so here in my definition I have another new word which is moment map. So next step would be to define a moment map for symplectic action. Okay, so if you have an action of group G, so G action kind of reduces the action of Lie algebra of G on M. So that is essentially kind of if we have an element, say L here, we can look at one parameter family or one parameter subgroup G equals exponential of KL, and then we can act with this element like construct phi for this E of KL, and then kind of look at derivative of this phi at t equals 0. So we are kind of looking at an action of group elements that are near identical. So that will give me some map phi L and M. Okay, so now, yeah, I need to make one more step. Let me write it. So if I have this infinitesimal action, yeah. So this infinitesimal action. Okay, so this okay, so this infinitesimal action phi L, it kind of defines me the following thing. So I have Lie algebra G here, where my elements L live, and for this Lie algebra element, I can define a kind of a diffeomorphism which is also close to identity. So therefore, an element L here will define me a vector field VL that is in vector field of M, which is essentially a Lie algebra of diffeomorphism. So previously, when I have group action, I kind of define it. So that is essentially a homomorphism of two groups G into diffeomorphism of M. So for every element G here, I have an element from diffeomorphism of M, like invertible smooth map phi G, and then this kind of preservation of composition structure. So composition is multiplication of diffeomorphisms, and we want a composition or multiplication in a group G to be compatible with composition in diffeomorphisms. So it means that we want this map from G to diffeomorphism of M to be a homomorphism of group. So now, if I consider Lie algebra for G, or I consider this infinitesimal diffeomorphisms that are close to identity, that originate from a group elements that are close to identity, which are exponents of TL. So I will get a map. So this phi L is essentially like, yeah. So this element is like identity diffeomorphism plus summation of a vector field, and here we also take d of dt, and we will get a vector field. So essentially, from an element of Lie algebra, we get a vector field which is infinitesimal version of a diffeomorphism on M. So now we can kind of ask what became to this condition of symplectic form preservation on the Lie algebra level. And on the Lie algebra level, the preservation of symplectic form is basically a statement that for every element of Lie algebra, we take its vector field, and we ask the following condition, that derivative with respect to this vector field L preserves the omega. So let us use Cartan formula that expresses Lie derivative in terms of de Rham differential and a vector field substitution or exterior derivative. Oh, sorry, interior derivative. So vector field substitution. So it has this nice formula that we can express LV by kind of this kind of composition of operations. So we can first apply de Rham differential or exterior derivatives and then substitute vector field in a new form, or we can do these operations in reverse order, and kind of the addition of these two expressions will be the same as an action of LV. So why this formula is useful? So here rewriting IVL plus IVLT acting on omega. So here I can use the following property, that my symplectic form is by definition the closed to form. So therefore, for closed to form, only first term survives. So it means that my condition of preservation of symplectic form under infinitesimal action of the group became with condition that this one form, IVL of omega, is actually a closed one form. So then, given some additional assumption that our symplectic manifold has trivial first de Rham cohomology, so given this, so that in particular implies that every closed one form, so lambda from omega 1, and so every closed one form, for if alpha is closed one form, means that there exists some kind of function lambda, function f, such that this closed one form is d of some function. So this condition will be automatically satisfied in our cases, because in our cases the m's that we want to use for our symplectic reduction are just kind of remark for our applications. So m is just complex numbers, so Cartesian product of t to some power, and this all these spaces, they are kind of trivial for cohomology. So every kind of hk for these spaces, they are zero for k bigger than units. So we only have H top, which is non-zero for these spaces, but because they are connected and have single component, while all higher cohomology groups, they are trivial, and in particular that implies that H1 is trivial. So every closed form on these spaces is exact. So, or in a kind of more general setting, we make this assumption, and that immediately implies that IVL omega is d of some function, and usually in the symplectic geometry literature, this function is denoted by h, and to indicate that we have for each element of Lie algebra, we have its own function HL, H, so we kind of indicate a subscript that. So we can say that HL is kind of a map from the algebra to functions on M. So we take element here and map it to HL. Yeah, okay, maybe I should call this thing a different letter. Let me call this kind of canonically letter G. So, kind of let us recall. So we have for Lie group G action, we define it an action of Lie algebra, which gives me a kind of vector field for every Lie algebra element. So then preservation of symplectic structure under this assumption that H1 is trivial means that the substitution of a vector field into symplectic form gives me an exact one form that is d of some function. And for different L, we have different functions, and therefore this kind of map from L to VL to HL gives me eventually a map from Lie algebra element G to a function on M. So map G applied to L is just this Hamiltonian HL, which exists by this construction.
Sorry.
Yes.
Why HL is a function?
Yeah, HL is a function. So for fixed L, HL is just some function on M.
Yeah. So iota VL omega is a one form.
No, iota of VL. Yeah, iota of VL omega is a one form. So it's a one form that is closed one form. Because we demand this condition. And then because we have no first cohomologies, it means that every closed one form is exact one form. So it means that for every closed one form there exists function for which this one form is d of this function. And then we kind of take this function. So for each I omega L we take the function, and that gives me a map from VL to a function, and then I can combine it with a map from L to VL to get a map from Lie algebra to functions on M.
Excuse me, the first, the round cohomology is equal 0 is assumption or conclusion?
So that is assumption for this thing to hold. So that is assumption for this implication to hold. And we kind of make a remark that in our cases when we want to apply the symplectic reduction, this assumption holds. So we want to apply the symplectic reduction to quotients of C to the power n. And these are spaces that don't have first cohomology. So this kind of assumption is required for this implication. And for this, we kind of given that this holds, we can define a map J.
And this HL may not unique.
Yes, so as usually we can shift our HL by some constant. So what is a non? Okay, so it's a good question about non-uniqueness. So here, like given that HL is defined by this equation, we can say that we can shift kind of HL by a function which which is annihilated by exterior derivative. So that is the function that is d of this function is 0. And because our spaces are not compact spaces, but okay, but I think for complex numbers, like the only freedom is shifting kind of HL by some constant, and that would give me some kind of overall freedom in defining this HL. So generally,
how to construct this J continuum? It should be a linear map.
Yes, that it should be a linear map. Yes, so on the Lie algebra we have two structures. So we have like structure of linear space. Yeah, I think here if we choose a basis in this linear algebra and construct a map of the basis, so then by linearity we can define a map on the whole algebra. Okay, so and this map is what is called moment map that we used in this kind of description of this symplectic quotient in words. So okay. Yeah, so now the next step is to kind of explain this level view. Right here. It's fine. Okay. Okay, so let mu be an element okay, now you can yeah, I think I got a bit confused because here I actually want this thing to be a dual algebra. So what I want to say, I want to say the following thing, that here it's not kind of G applied to L, but it is canonical pairing between I would say just like now. I think it should have. Yeah, okay, let us do the following. Let us make a break right now, and while I'll think why there should be a star. So I think the proper moment map should be mapped from G star to this thing. So let us make 7-minute break till 11. Well, I will check my other, get myself unconfused. So we will talk more about this formula after the break. So let us make a break till 11. I will be back. forget it myself. Yeah, so here we just kind of having kind of vector field that defines a function. So indeed defines a map from G to functions on M. So now let me introduce another map J that will be a map from M to a dual Lie algebra of G. So that will take like a point on M and give me the algebra L. So then, given this map, I can construct a kind of Hamiltonian or this HL in the following way. So I can say that my HL, so it is function. So function means that it maps. Okay, so HL itself maps a point in M into some real number. So we can realize this map from point in M to some real number HL of M, HL of P in the following way. So first we take our P and map it using this map J, map it to an element of dual Lie algebra. So that is G star. So we take the map J from M to G star. And then on the G star, we have a kind of canonical pairing that allows me to kind of take an element of G star and take an element from Lie algebra G and map this pair to a real number if it's real canonical. Okay, so Lie algebra over real numbers. So G of L canonically paired with L. So this records kind of canonical pairing for this star from G into their basically to real numbers. So that would be my moment map. So I will assign a map from M to G star such that for every L kind of HL is kind of G canonically paired with. So that will give me a function on M, because J will map a point on M to G star, and then with additional element of L, it will give me a number for every point. And then this J is what we call moment map. So now for this moment map, we have an additional condition, so which I kind of suppressed here because it's usually suppressed. But let me restore it because in some cases, even when we have kind of abelian group acting on kind of some complex numbers, so this action may not be what is called equivalent. So if I have group G, so group G has some natural action on its Lie algebra. So and this action is kind of realized in the following way. So if I have so first I consider adjoint action of G, adjoint action of G on its terms. So it means that we are doing the following thing. So we take element V of G and another element H of G, and for kind of all G, we define the map of this second copy of G in the following way. So we map every element to its conjugated, okay, G minus 1 HG. So the subjoint action is an action by conjugation. So now I can kind of use this adjoint action to induce action on Lie algebra. So here, instead of arbitrary element of a group, I can consider an element which is kind of close to identity. So this is kind of 1 plus xi plus dot of xi. Here is an element from Lie algebra. So then I can conjugate this xi. So I will get t minus 1 e to the xi g. So that will be once again a group element. Furthermore, this group element will be close to identity. So it will be identity plus some other t correction. Because here if xi is 0, so this conjugation preserves the identity. So therefore here I can do the following thing. So I can compute this linear term in t just by applying d over dt derivative at t equals 0, and I will get some kind of a new element by action of g, and this element is kind of usually called denoted. Okay, now whether it's a with a large or with a small. Moment. Yeah, I think because it's still action of a group on the other, I think it's ADG applied to this element. So here, kind of from a joint action of group on itself, we can induce a joint action of a group on its element. And then similarly, we can use a kind of non-degeneracy of a pairing on G and G star to introduce kind of dual or adjoint action on congruent elements. So let me call L. So what we want that for every kind of pair of okay, so I put the G star element first in my bracket, so that's why I consider this pairing, and I want this pairing to be equal to the following thing, so this pairing of L with a joint action of this constant. So given this adjoint action on xi, I can induce linear transformation. So adjoint action will be some linear transformation on xi, and I can induce a kind of conjugated to this linear transformation as a linear transformation on linear forms on xi, and that will give me kind of adjoint action on dual algebra. Okay, so and kind of we started with action of a group G on M. Okay, this is some symplectic condition. So that allows us to, let me erase this one. I need to erase. So that allows to ask the following question. So given element G from G, I can do two things. So I can, let's kind of M be point in M. So then I can transform this point by applying a diffeomorphism associated to this element G. So having a group action G on M, also action G on M, it kind of gives me this map that will transform points on M into some new points parameterized by G. So also given the same element G, I have kind of this adjoint action G on G star. So that will take kind of element of a dual algebra or linear form on a Lie algebra and map it to SGL. And kind of my moment map J was a map from E from M to G sum. And what we now observe is that on one hand we have G action here. So that is this G action. And we have another G action on the field. So another G action field. And then there is a natural question like whether these two actions compatible. So
it should be a rank G star, right?
yes. Yeah, so then we call J star equivariant moment method. We call moment method. Variant moment method. If the following holds, so if kind of J applied to IG of M, so if we first kind of act with a G on M and then apply map G is the same as if we first apply map G, get an element of a dual algebra, and then apply this adjoint action on a dual algebra. So that is this equivariance condition for a moment map. And to just emphasize that it's not non-trivial condition, because usually, especially in the physics literature, people kind of omit all this business altogether about equivariance. But it turns out that in some simple cases this equivariance can be violated. So let me have an example of non-equivariant moment map. So we will just use this example of non-equivariant moment map, and kind of for rest of our discussion, all moment maps will be equivariant, and that will be like almost obvious to see or very straightforward. So let me example. Okay, we will. Okay. So let's take my M to be just two-dimensional real space, and we will use kind of physics notation that it will be kind of coordinates and momentum. So coordinates on one copy of R is X, and coordinates on second copy of R is T. And reflective form is just simple. Okay, so let me just to keep science aligned with my notes. Let me choose reflective form dpdx. So that is also closed to form. Okay, so we're in two-dimensional space, so every two form is closed form, but this form is also non-degenerate form. So in this basis, the coefficient is just 1. So let me consider group G, which is also R2. Let me kind of give a coordinates A and B that will kind of label my elements of G. And here G is kind of R2 group under translations. So under translations means that the kind of group structure given by the following relation. So if I have pair of elements A1, B1 and A2, B2, then kind of group composition will be A1 plus A2 and 1 plus B. This composition is kind of associative for obvious reason, because addition on real numbers is associative, and it is okay commutative. It has inverse, which is minus A. Say minus B, and kind of 0 is an element 0. So that is my Lie group G. So it's a group which is a manifold. Okay, so now let me consider an action of G on M. And the action is once again by translations. So an element AB acting on kind of point Px on M. So the action is just distance B by A. Okay. Double check with my notation, so I would match notation with the node X plus A equal. So that is actually by translations, and it's kind of a straightforward reason. It's clear that that it is kind of homomorphism of groups. So here, if I kind of compose it with another action by prime B prime, we will see that it will be just addition of X plus A prime, P plus B prime, and that is the same as shifting X and P by a sum of A prime and B prime. So this action, okay, is kind of proper action. So then the next step is to check whether this action is symplectic action, whether it preserves symplectic form, but that is also straightforward. So we just kind of transform our symplectic form from phi star for element AB applied to the symplectic form is straightforward. So we just kind of substitute P plus A, so P plus B, and B X plus A. So A and B are just some constants, so we fixed this element, so they're constant, they're standard, they depend on P and X. So that's why here we just got which is omega. So indeed, this action is Hamiltonian, or symplectic. That's symplectic action. Okay, so far so good. So now, what is infinitesimal action? So kind of, okay, so here Lie group is just R2 itself, but just to distinguish different elements, we do alpha and beta kind of coordinates on this R2, and the vector field that we get from the algebra element alpha and beta is nothing but alpha d over dx plus beta d over dx, d over dp, kind of standard basis on tangent space to this two-dimensional. So that's standard basis vectors. Okay, so we established a kind of map from the algebra to vector fields, and kind of here, okay, let us, because one example of everything, so let me be more kind of detailed. So that is my vector field. So once again, it's kind of straightforward to check that Lie derivative with respect to vectors for this vector field preserves the symplectic form. But we can do even better, so we can just guess what should be the Hamiltonian. So let us just substitute, okay, this vector field into symplectic form. So what would we get? So if we substitute alpha d over dx into this symplectic form, so we will get minus alpha p, and if we substitute beta d over dp, we will get beta dx, and that happens to be d of minus alpha p plus b times. So that kind of up to overall constant gives me this fact that h for Lie algebra element alpha beta is minus alpha b plus b times. Okay, so that's good. So now next step is a moment map. So moment map was kind of mapped from M to G star. So M in our case is just R2. Okay, G star also happens, like G itself happens to be R2, and dual Lie algebra is also R2. So how this map works? So we have a point xp on x, and we want to map this point to some element of a G star such that that G paired with element alpha beta, let's say alpha G1 plus beta G2, that this thing kind of matches with our Hamiltonian function h alpha beta minus alpha b plus beta x. So that gives us a kind of immediate form for this map. So we should choose J1 to be minus b and J2 to be just x. So that is our moment map. So it maps xp to minus bx. Yeah. Okay, so we have a moment map. So now because so G is a Millian loop. So the kind of adjoint section of G on G is trivial. So I will need to compute G minus 1 H T because everything is abelian. So H G compute. So G minus 1 GH is H. So the group action on G is trivial. So therefore it's trivial action on the algebra. So that means that X star G is kind of trivial action, and on the algebra, trivial action means that text by zero. So for every element size from the algebra, from G, okay, every pair in G and J star. So this thing is okay. So that is good. So it acts on kind of G star trivially, but what about action on M? So action on M. So here we have like our vector field which gives me infinitesimal action. Okay, and we have this final. So let me. Yeah, I need to erase something. So yeah, erase that part. Yep. So let me erase this part of this definition. So I will keep the most important formulas which agree. So let me check this equivariance condition. So let me take my point M, the point xp. So if I act by phi AB on a point xp, so here it's x plus a. Okay, I have it written here. So x plus a, b plus b. So let me then apply j to phi AB xp. So that is the same as applying j to x plus a b plus b. And kind of by construction, j applied to point x and p is minus bx, minus b minus b minus x, x plus a. So that is my moment map applied to a transforming point with respect to this g action. Okay, and this thing is, and Sorry. Sorry. Trivial action means that it's reversal. So I'm going to start for all G of psi is just psi. So if you have G of Px, that will give me exact again G of xp, G of xp, which is minus Px. Now we notice that this yellow expression, which ends up with minus Px, is actually different from this red expression that is minus Px, but is shifted by minus Ba. So that for this expression we observe that A phi of G of M is not equal to so that is an example, as I kind of anticipated, example of non-equivariant moment line. So even in kind of so trivial case, then the action is kind of very boring abelian action by shift. So the moment map may not be equivalent. However, in kind of cases that we're going to consider, in particular, what we want to apply this construction. Yeah, so we want to apply our construction to the case that M is P to some power and G to the power S. So in this case, we will see that the action, which I haven't carefully specified, but in this case, the action of this G is the following. So we have kind of complex coordinates G Z1 to Zn plus S, and the G action basically multiplies this Z coordinates by various faces. So let me call it, let me call A an index that runs from 1 to n plus S. So then the action of this whole G on a coordinate ZA will be multiplication of ZA by the following phase. So we will introduce weight vectors. So this phi alpha, they are just elements of U1, which is 1. And so these are just faces. Okay, let me put I here. This is R over 2 pi d. So it is kind of real faces up to 2 pi z identification. And this W alpha A, yeah, I think in my notation I have capital A upstairs. So let me kind of try to keep my notations aligned. So this W phase, they are just some integer numbers. So that is kind of our action of G on M. And for this action, the moment map would be equivariant. Let me kind of return to this example after I kind of explain the full construction. So let me not kind of get into this example in detail. So wait for a minute. So we explained it, this notion of equivariant moment map. So then there is another word, level mu. So we have this moment map that is equivariant. Okay, so now the moment map is a map from M to G star. So let me take mu, which is just some element of G star, and then we can consider a kind of subspace in M, which I will denote M subscript mu. So that is essentially points in M, such that moment map of these points equal to our fixed level. So that is kind of level mu moment map subset. So that is kind of subset of M, and furthermore, so there is some kind of lemma for regular value mu, so which is an image of this moment map. So okay, so typically moment map may not have an image of the full G star. So then this subspace might be just empty subspace. So however, for some mu which is regular value, so this kind of image of map is kind of typically contains some corners and singular points. So if you take like a usual regular interior point of this image, so then this kind of M mu is submanifold of. Okay, so we have this submanifold of M. So then there is kind of second result. So here I'm kind of given this lemmas without proof, because that's some kind of standard result from symplectic geometry, and I will just kind of add proofs to lecture notes. But just for the sake of saving time, so I'm giving them without proof. So then there is a G action. So M mu action, and that is kind of property of the moment map equivalence. So admit G action given. Yeah, let me give it here. So if my kind of level of a moment map mu is such that it is invariant under this adjoint action, so for all G, this kind of moment map is preserved. So one example of such mu is mu just equal to 0. So G star is a vector space, so it has zero element. And for 0 element, like if I apply any of this dual of adjoint co-adjoint action, okay, or 8 star G to 0 will give me a 0 element again. So if I have mu that happens to be preserved under this action, so then or if say G is abelian, so then this thing kind of holds for all elements of G and for all values of mu. So then M mu itself admits G action, and that's kind of consequence of equivariance. So recall that the equivariant basically tells us that G of phi G of M is at star G of G of M, and if at star G of M kind of acts trivially, so that means that the G action kind of preserves the level of a moment map. So if G of M was some fixed value, then G of phi G of M is the same fixed value. So equivariance implies level preservation. Okay, so we have this equivariant moment map, so it preserves the levels. So then kind of more complicated part of the result is to show that this action is free and transitive. So that was kind of so kind of more complicated lemma that requires some technical tools to prove. So technical lemma. So that was conceptual lemma that the G action kind of extends to level set of a moment map, and technical lemma is that this G action is free and transitive. So basically it means that there are no fixed points of this G, and all elements of G acts in non-trivial way. So then kind of we define a space which is the literature called M reduced, which is the following thing. So we take this level of a moment map and just kind of look at the space of G orbits. So that is space of G orbits. So this space, kind of this lemma 2 implies that this space is defined, and the technical lemma, so technical lemma basically allows us to say that this space of orbits, or M reduced, smooth symplectic means. So to kind of okay, let's just say smooth manifold. So that's where we need action to be kind of free and transitive. So if we relax this assumption, then in general that will be not smooth. It will be like singular manifold or some kind of more complicated object, some collection of orbits that don't glue nicely. But and this action is usually free and transitive, and that once again follows from this kind of regularity of mu. So if you choose kind of good mu, which kind of lies inside of this image, not at some boundary or some sort of singular point of this image. So if we just take a normal point in the interior, then this action will be free and transitive, and this quotient will be a smooth manifold, and furthermore, it will be a smooth symplectic manifold, and symplectic form is defined in the following way. So given this motion, we have a quotient map that maps points on M mu to the corresponding kind of orbits. So take a point and map it to orbit on which this point lies. So then, having this map, we can construct a pullback map by stars that will take, so it pulls back and forth on M mu mod G. So without the degree, so it pulls it to K form on M. So in particular, if we have a two-form kind of downstairs on this space of orbits, we can pull it back and get, so let's say that is some two-form on the space of orbits. We can pull it back to a two-form on this level set of a moment. And then furthermore, this pi star it kind of computes with D, so kind of takes closed form to closed forms. So that part is nice. And now, yeah, okay.
Sir, I'm still confused with this technically. The mu is arbitrary.
Yeah, it's kind of arbitrary inside point. So we will see in kind of in a moment an example that the typical image of a moment map would be some kind of polygon or polyhedra. So and for this polyhedra you have like two types of points. You have kind of nice points inside where kind of sort of open set around this point is just r to some power. Or we have like a boundary points or corner points. So I'm just saying that if you don't take these corner points or boundary points and just take nice inside points, then regardless which point you take, the action would be free and proper. And furthermore, this M reduced will be kind of for all mu's which are inside points, they all will be isomorphic.
But it's in different chamber. It can be in different chamber. It can be different.
Let me see. So you're saying that I might have something like gluing of two polyhedra over something like H and have like. Okay, that might be true. Okay, so I haven't thought about it, but that might be true. That if you kind of have some kind of H which separates two chambers, yeah, then the answer might be different. But I think in all our applications, the image of a moment map will be just some kind of polytope, and that's why there will be no different chambers.
And this mu, if this mu should satisfy the condition in lemma 1 and lemma 2.
Yeah. So in our case, as we see, we will apply it for G, which is U1 to the power S, and in this case, Lie algebra is just R to the power S, and that is abelian Lie algebra. So it has trivial brackets. So therefore here, for any value of mu, this condition will be satisfied because our group is abelian. But in a general situation, yes, like there are two options. So either you choose like a specific mu's which satisfies this condition, or you choose some smaller subgroup that preserves a particular mu. So that is also option that you here you take a quotient. So then this mu would also acquire subscript. This G would also acquire subscript mu, and that would be like a subgroup of G that preserves given mu.
And this G action is transitive on M, right?
Yes. So given that mu is kind of regular on M mu, so it's kind of free and transitive on M.
So transitive on M mu. I mean, if it's transitive on M, the M mu will.
Yeah, automatically transitive. Yeah, that's. Okay, I think here kind of important part is that there are no fixed points, so it's kind of free action.
Yeah, but why we not quotient G directly? Why we should
not quotient G directly?
Yeah, if G action on M is free.
Because we kind of want to get as a result we want to get symplectic manifold. And symplectic manifolds, they're kind of even dimensional manifolds, and Lie groups can have arbitrary dimension. So if I just look at the space of orbits M over G, that dimension of this space will be dimension of M minus dimension of G, which might be both even and odd. So if I take, okay, so if I just consider, say, R2 with some U1 action, so R2 just complex numbers with U1 action, that is just rotation by phase. Okay, so this action is not free. Okay, so let me remove 0 to make it free. So then I can I can evaluate this quotient, that will be smooth manifold, but this smooth manifold will be just a real line. And real line is not symplectic manifold. So the kind of key point of this construction is to kind of start with one symplectic manifold and obtain as a result another symplectic manifold. So that kind of require us to sort of subtract dimension of group twice. And that's kind of how we do it. So first we roughly subtract dimension of group G by imposing this moment level set, because this will give me like if we pretend that it's just algebraic equation, that will give me a number of constraints equal to dimension of Lie algebra. So that will reduce, that will make like M mu a manifold of codimension dim G. And then the second quotient of this M mu over G will give me M whose kind of codimension will be 2 times dimension of G. So that means that we kind of go from even dimensional M to another even dimensional manifold whose dimension is smaller than twice dimension of G. So that is kind of part of the construction, that the result that we desire to get symplectic manifold. And in kind of our setting, the result that we desire is to get, like, once again, a variety over C. So and therefore, if you have like action of some kind of real group here, then we need to kind of subtract the dimension twice. But this kind of theorem that relates GIT quotient by symplectic quotient. So here the quotient is just ordinary quotient, but by the action of complexified group. So it means that we subtract once again twice dimension of a group, and this space is the same as kind of performing symplectic quotient when we subtract this twice dimension in 2 steps, going to level set first and then quotient in level set by G again. Okay, so we have this pi star map that allows us to lift a form on M mu to form a quotient to form on M mu, and also because this level set I mu is given by some collection of equations, so we have kind of embedded map. So I mu is embedded into M. Embedded as a smooth manifold, smooth submanifold. So therefore we can take a pullback map with respect to this embedding that will kind of pull back a form on M to a form on M mu. And we can take our symplectic form on M, so M was symplectic manifold, and pull it back to symplectic form on M mu. And then we can do the following thing. So we can define our 2 form on reduced subspace, reduced space by the following formula. So it will be a 2 form whose pull back to M mu using this canonical projection map is identical to a 2 form that we pull is identical to a pullback of symplectic form on M. So in this definition, kind of, so it's not some kind of equality is atomically reduced equal to something, but in principle, like for this projection, we can choose some section and use this section map to compute omega reduced. Also, it will not be like a canonical way, because there are many kind of section maps. So this formula is canonical, but using a section map, we can essentially invert this projection and compute omega reduced. Okay, so that is kind of so that is the reason why we call this thing symplectic quotient. So it kind of takes a symplectic manifold into symplectic manifold. So this mu, which is subscript of these double lines, is a choice of level set, and if this mu is suppressed, that kind of typically is assumption that mu equals 0. So if you just have double lines, that is the same as it's kind of assuming that we perform symplectic motions in this kind of special point mu equals 0 that always belong to a dual algebra. Okay, so now I kind of finish the definition of this symplectic motion. And this symplectic motion construction turns to be a very useful construction for toric varieties. Yeah, so let me give you kind of an example of what kind of moment map we get and what kind of image of moment map we get and how to have a combination. Okay, so here we say that our is u1 to the power s and gx multiplies our complex coordinates by a phase that is some linear combination of this kind of group elements with integer coefficients. So they are just collection of integer coefficients. Okay, so and we kind of already wrote the symplectic form on one copy of C. So on one copy of C, the symplectic form was dz times dz bar. And if we have multiple copies of C, which is, and then our space is Cartesian product, so then we can just take a symplectic form on Cartesian product, which is just sum of symplectic forms on each of the components. So now what we do, okay, so we substitute the vector field. Okay, so in our case, phi will be okay S1, which is phi alpha belong to S1. But I think we can use the same phi. Sorry, maybe I should be more careful. So let me say it the following way. So e to the I phi alpha belong to kind of i's copy of S1. So and which is U1. So U1 is kind of a group formed by phases, by kind of complex numbers with absolute value equal to 1. Kind of canonically, so that is kind of canonical definition of U1, just complex numbers whose absolute value equal to 1. So they are just pure phase. So it means that this psi is of the form e to the I phi, where phi is just some real number. So therefore, kind of e to the phi, e to the I phi, they are elements of the Lie group, and we can consider phi itself as an element of a Lie algebra. So therefore here, okay, so the vector field, okay, so we have this section, and now if you want infinitesimal action, then we should look at kind of term which is linear in phi, and for infinitesimal action, the vector field would be the following. So we take the kind of ZA, and we kind of shift it. Okay. So infinitesimal delta ZA would be ZA plus multiplied by alpha. So for the A, it will be like the A d over the H. Here is just WA alpha by alpha dA d over dA. And here, like if you look at this action on complex conjugated coordinates, I5, so on complex conjugated coordinates, so there will be kind of complex conjugation of this action of d bar A d over d bar. And here, okay, so we have film summation. So that is kind of vector field that describes an infinitesimal action of this multiplication by a face. So now we can like plug in this vector field into our symplectic form. So that is kind of rather straightforward. And then what we will get, let me here like suppress indices and just give you a schematic expression. The schematic expression will be something there will be double phi term. And then if we substitute z over dz into symplectic form, we will get something like z. Z bar d over dv, and if we substitute z bar d over z bar piece, we will get z d over z bar from the first term, and from the second term we will get z bar dv term, and that will kind of combine nicely into d. Okay, so omega phi just some w phi just some constant, so they are independent. But here all these d's kind of combined into absolute value into d square with some. No, I don't think I have vector of half. Where do I have vector of half? Okay, give me a second. No, I don't have vector of half. And some kind of careful computation with kind of coefficients. Okay, maybe I missed vector of half, but I will kind of fix this in my lecture notes. So h phi. So now it's summation over a, additional alpha, alpha w alpha. Absolute square dA square with some coefficient here which I wasn't careful, maybe some sign or some half. But kind of up to this overall constant is just phi alpha w alpha absolute value d square. So that is kind of Hamiltonian, and the corresponding moment map that maps F, it is some copies of C, so it maps into U star, which is just F copies of R, is essentially in the following way. So we have kind of coordinates, point with coordinates A, and this point mapped into, so here we for fixed alpha, so alpha runs from 1 to s. So that will be the first component will be W1 sum over A, W1 0 square, and for the second component will be W2 A square goes away to WS so that is kind of moment map for this section. So moment map, and here let us notice that kind of given. So given that this way, all of these weights are positive. Okay, so given that all weights are positive, then kind of image of the moment map would kind of lie, would be just kind of positive factor in this S-dimensional space. And therefore, so this thing is kind of typical manifold with corners. So in two-dimensional case, it looks like this, and it has like interior points, it has boundary points, and it has like one corner point. And in higher dimensions, you just have like a more structured, like corner points of different levels. Okay, and what we want to kind of work with these interior points in this case. So kind of basic example to keep in mind. So we started this symplectic quotient construction motivated by x equals p1. So let us kind of reproduce CP1 from symplectic quotient construction. So we take n equals s equals 1. So that gives us kind of our n to be a C2. And we choose, okay, so we have only one dimensional action, so there will be like one weight vector. So this WA weight vector, we will choose it to be just 1, 1. So that corresponds to action V1, V2, just multiplied by a same phase. We take the point Z1, Z2 and multiply both coordinates of this point by a same phase. So that will give weight vector 1. And in this case, the kind of moment map will be, okay, so G star is just real line. So moment map will map point Z into absolute value Z1 square to absolute value Z2 square. So, and that here is kind of tricky part that if you naively kind of take sort of usual level of a moment map, which kind of always preserve it under adjoint action, like mu equals 0. So for this kind of moment map, mu equals 0 is not a regular quotient. So usually in the literature, people kind of cheat a little bit. So they kind of secretly put some constant here, like put some kind of constant -1 here, like for arbitrary reasons, like just kind of arbitrary put a constant, and then mu equals 0 is perfectly fine kind of interior point. But without this -1, so without this yellow addition, like strictly speaking, doing the standard reduction at mu equals 0 would give you like non-smooth manifold, because that is not a regular way. However, in our kind of construction, we can do reduction not necessarily at mu equals 0, but arbitrary value of mu. So in our case, like if you don't do this yellow addition, we can just choose mu equals 1 or mu equals any real positive number. So mu equals negative number is not in the image of moment map, so very pointless to do a reduction at this point. And mu equals any positive number. Let me just keep it as a parameter. So t is just positive real number, and that's kind of where we would do a reduction. I think I don't need, yeah. So mu equals t. So now what will be kind of submanifold the fixed level set? So that's kind of level set mu equals t. So level set is what kind of set of points. Property. One complex number. And this subset you can immediately recognize that this subset is isomorphic to S3. So it's three-dimensional sphere sitting in this four-dimensional real space, which we can also think of two-dimensional complex space. Okay, so then on this S3, we have and the kind of T is essentially square of the radius of S3 of radius R, and R square equals to T. And that's why we want T to be positive and non-zero, because for T equals 0, this sphere is not a sphere, but so on S3 we have kind of U1 action. So once again, given that Z1 and Z2 satisfy this condition, so if I once again multiply Z1 and Z2 by a phase, this pair would still satisfy this condition. So that is my kind of U1 action. So it takes Z1, Z2 and maps it to once again Z1, Z2 multiplied by phase. Okay, and then kind of our reduced this kind of motions of S3 modeled by this U1 action, and the orbits of this U1 action are just two-dimensional spheres, and furthermore, you can kind of perform this orbit identification using some holomorphic coordinates. So that's why you can get not even S2, but kind of S2 with a complex structure SCP. And the reduced symplectic form. So once again, if you introduce carefully some coordinates, introduce this projection, embedding maps, compute everything. So then in kind of yeah, maybe I should kind of give you this embedding coordinate. So let me see. Let me. I think for completeness, I need to give a project. So let me kind of parameterize points on this level set in a following way. So let me parameterize these points in the following way. So let me take a complex coordinate Z and do the following thing. So look at the Z divided by 1 plus Z squared, and take another point okay, and I need some phase. Okay, so let me say R square R here, R square yeah, I think I can almost. So let's take R divided by 1. So here I will write it like this: b to the I pi just like that. So that will be parameterization for Z1 and Z2, and you can check that the points. So it is kind of three-dimensional parameterization. So I have like a complex number Z, and kind of some weight psi. So it's kind of three-dimensional parameterization, and for kind of any complex number c and any real number psi. So this kind of collection of points, it lies on this level set. So given that E equals R squared, and then, okay, given that we identify Z modular, psi modular 2 pi Z, I think that will give me a kind of one-to-one parameterization that every point here has this form for kind of unique value Z and psi. Okay, and then kind of the action of U1 action will be very simple in this parameterization. So it will just shift psi by psi. And kind of the orbits of this action are also very easy. We just say that now we drop the psi dependence, and therefore orbits of this action would be parameterized by Z. And in the Z coordinates, the reduced symplectic form will have this very simple expression, dz bar. Okay, modulo some numerical factor that I will be careful, like 2i or I over 2. But kind of Z dependence has this structure, dz bar divided 1 plus Z bar squared, and then what is known as Kubinic 2D form. Which is some kind of nice round to form or nice round representative for two-dimensional cohomologies on P1. Okay, and that is kind of, so it is non-degenerate. So even kind of at a patch where Z goes to infinity, so if you make transformation like W equal to 1 over Z, then because of some terms in denominator, you would still get a kind of non-vanishing expression even when Z goes to infinity. If you kind of properly transform this form to a different patch where Z going to infinity with some other coordinate going to 0. So that is kind of CP1. Okay, that was CP1 example, and higher dimensional examples are kind of work in a similar way, that we will impose a kind of independent level sets for each of components of a moment map, and then we will quotient by U1 to the power n. Okay, and in your homework there will be like several exercises where you will be asked to compute symplectic quotients for some kind of given weights. You will be asked to compute symplectic quotient and to kind of identify the resulting space as some kind of familiar manifold. Yeah, so now in last 15 minutes I want to say one more thing. So our original goal was to get some sort of combinatorial description of toric variety. So this symplectic quotient, in general, it kind of allows us to construct toric varieties, and the reason for that is that first symplectic quotient related to this GIT quotient, and for GIT quotient we essentially start with Cn plus S that have a kind of an action of a large torus like C star n plus S. So then we subtract a kind of some orbits of a lower dimensional torus C star to the power S, such that the quotient is smooth, and then on this quotient we still kind of have an action of a kind of remaining torus like C star to the power n, and that's why this GIT quotient procedure kind of naturally gives you toric varieties, and we can realize this GIT quotient as a symplectic quotient and therefore the data for symplectic quotient is kind of collection of this integer weights down. So that in principle allows us to kind of package the data about our toric variety in the following data. So we just provide a collection of kind of weight vectors WA alpha. So it's just some S times n by S matrix. So we have like S, n plus S dimensional vectors, which are these weight vectors. And then we provide like another piece of data, which is level of a moment map. And this piece of data, it kind of gives us sort of weak dependence in a sense that as long as this mu is kind of regular value, then we get an answer that is independent of mu. So this mu is like, okay, so it's like a data that ensures that we still get like a smooth variety, but if it's smooth, nothing would depend on this data. So, and essential data is just a kind of collection of integer vectors, like S integer vectors in n plus S dimensional space, which is the weights of U1 to the power S action on C n plus S. So on one hand, that looks like combinatorial data because we kind of encoded our toric variety in terms of some finite collection of numbers. However, we want to do better because for kind of drawing tropical curves, we really need to kind of get a bit more kind of geometry from this pure combinatorial description. And to do this, let us kind of once again recall our original definition of a toric variety. The toric variety was kind of complex variety with an action of complex torus, such that it contains this complex torus as a kind of proper subset. And in our examples for toric varieties, like complex plane or CP1, it was essentially a kind of gluing of a kind of torus itself or kind of proper open set, and then you kind of glue it with some additional lower dimensional orbits. So that was kind of schematic construction for TP1. So we take this algebraic torus, proper subset, and then we glue 2 points, like point at 0 and point at infinity, to get CP1. So that is kind of one-dimensional orbit of this star, and here we have pair of dimensional orbits. And you can imagine that if you kind of take some orbits of C star to the power n, like say take a top orbit, like a full C star to the power n, and then kind of start gluing in to it some orbits of a lower dimension, then in some situations you would get like a toric variety. So kind of schematically, toric variety X would essentially toric variety X of complex dimension n is essentially C star to the power n with or partially compactified by orbit of lower dimension. Like in the case when we get some kind of compact toric variety, and that's a variety on which we want to look at the Gromov-Witten theory to avoid kind of intersections to run away at infinity. So we want X to be compact. So therefore, for compact X, we need to kind of fully compactify C star to the power n, and to preserve the storic action, we should restrict our kind of compactifications by orbits of C star to the n. However, we can take lower dimensional orbits. So in the case of CP1, it kind of works in obvious ways. So we have C star itself, so that kind of as a real manifold, it looks like a cylinder. So it's kind of real line times a circle. So when we parameterize non-zero complex numbers e to the r plus I phi, so it is angle and real. So then, in order to get CP1, which as a real manifold is just a sphere, we can do the following thing. So we can take 2 points. So these 2 points in this r coordinates will be points at r equals plus infinity and at r equals minus infinity. So since we are adding kind of points at infinity, so we essentially compactifying the space by adding some limiting points. So if we add the points at infinity, then we will get a 2-dimensional sphere. So in this case, it's like adding points at infinity is like attaching kind of tiny cap to this infinity long cylinder. To this infinity long cylinder, we kind of attach tiny caps at infinity and get something which is topologically looks like a sphere, and you can do this attachment by preserving complex structures. So that's why it's here with a complex structure which is EP1. And you can imagine that we can generalize this procedure to a more complicated toric variety, that we can start with some C star to the power n and start gluing in some lower dimensional orbits. So simplest case would be, say, C square. So C square is a toric variety, so it's kind of a product of two, Cartesian product of 2 toric varieties like C cross T. But let us kind of see how it relates to C star square. C star square is just a torus, and then to this C star square, we need to glue in the following thing. So we need to glue in C star and another C star and the point 0. So that is essentially like an expansion of C star gluing back point at origin and some kind of Cartesian square of this expression. Okay, so we need to, okay, so that kind of works schematically, but it would be nice if we can get a kind of better description of this procedure of gluing in or partially or fully compactifying C star square. So let us notice that in this C star square, the part that is kind of really non-compact is a radial part. So angular part was kind of originally compact. So that's why let us just look at kind of radial part of this C star, which is kind of for every coordinate Z, we introduce this RA and phi A, and just look at subspace parameterized by RA. So we fix phi A's to some values and look at array. So for CP1, so this space of RAs will be just a real line. And when we do a kind of compactification to a sphere, so we essentially compactify this real line to an infinite interval. So we add like 2 points at infinity, minus infinity, and plus infinity, and that is infinite interval. So this infinite interval, okay, so it's now a compact space, and now kind of to see a sphere, we should kind of recall that for every point R, we suppress the face. So on top of every point R, we have a circle. So essentially this cylinder was a vibration of a circle over real line. So that was kind of trivial vibration or just direct product. But now when we added these compactifying points, we really added points, not circles. So that's why here we want the circle to kind of go smaller and smaller and shrink to a point when we approach this infinity or compactifying points at infinity. So that will give us kind of more geometric description of how we kind of glue in this additional orbits. So first we take kind of radial part, and then we compactify a radial part to some kind of polyton, so to make it compact. And then we kind of look at the circles. So in the interior point of a polyton, we have like some n-dimensional torus. And then as we approach kind of faces of a polyton, we want, for faces of codimension 1, we want one circle to shrink, and for faces of higher codimension, we want like multiple circles inside of this torus to shrink. And if I have a circle S1 inside of n-dimensional torus, so it has a topological invariant which is its homotopy type. So a circle inside of S1, so it is, so all the circles are kind of isomorphic to their homotopy type, and homotopy type is given by collection of n integer numbers. So that is homotopy type of the circle. And when we say a certain circle should shrink, we should say like what is the homotopy type of a circle that shrinks. And it turns out in order to this construction to give us a kind of complex variety, so we need some kind of consistency condition between radial dependence and angular dependence. So here, like let's say, in order to compactify a radial part, we introduce, so we say that compactification of Rn is given by some collection of hyperplanes at infinity. So let's say it like this. So HV hyperplane. So it means that so hyperplane is kind of uniquely parameterized by a normal vector. Or we can write down an equation for hyperplane is kind of a points in Rn such that that the product of a vector from kind of 0 to this point R, so that this vector is kind of orthogonal to, sorry, orthogonal to this vector of hyperplane. So we can say that this hyperplane is kind of spanned by linear span of the vectors that are orthogonal to its normal. Okay, so that is kind of hyperplane. Okay, so for general hyperplane, I think here so for hyperplane, I can look at kind of half space, which is half like hyperplane. It splits Rn into two half spaces, positive and negative half. So hyperplane splits Rn into positive and negative parts. So the vectors, the points that lie like, so if I choose direction of my normal vector, so for points that align in the direction of a normal vector and points that align in kind of opposite direction. So these guys, they are just points that satisfy inequality. B times R is positive, and here B times R is negative. So for any point R, there are basically three outcomes with this Cartesian product. So it's either 0, so we are on a hyperplane, or this product is positive or negative, so that we are to the kind of one side or other side of hyperplane, or belonging to positive and negative alpha. So we can construct compactification of Rn into a polytope by just taking a kind of intersection of a certain, okay, let me say which index I want to use. Yeah, I think I want to use A for this. So we take a certain number, capital B, of these hyperplanes, and then we say that compactification of Rn is just kind of intersection of this kind of positive subspaces of hyper. So in our kind of example, so CP1 is a bit too trivial example because hyperplanes. Okay, but let's still do CP1. So in the case of R, so that is the real line, and then kind of for this point at infinity. So hyperplane infinity, I need to provide a normal vector. So let me say that my normal vector B plus equals to a plus 1. So this normal vector just pointing like this. Yeah, okay. For this, let me choose B minus. So B minus is pointing like this. So B minus is minus 1. And here I took B plus equals plus 1. So that is my kind of radial coordinate. And now, so that is my H B minus is just a point. And now what is the positive and negative subset? So yeah, let me see. Maybe I should have give me a second. Okay. I think it's good. So okay. So here, because my B minus is kind of pointing like this, so if I take all vectors that pointing are vectors pointing like this, so then the product on this part will be negative, so that will be negative subspace of B minus. While this part will be positive subspace of B minus, and so that will be like positive subspace of B minus. And if I do the same thing with a B plus, then I will get a positive subset of B plus, and the intersection of two will give me exactly what I want. Will give me an integral.
So it should be bigger than 1. If it is bigger than 0, then it just
no, it's right. So it's so B minus times R. So B minus times R is just minus R. So okay, I see what you mean. So for minus R, yeah. So yeah, I need to shift by some constant. Yeah, that's a good point. So yeah, I should be more careful where my. Yeah, let me take here introduce some additional kind of number lambda. Yeah, and then here positive and negative will be like bigger than lambda and smaller than lambda. So then here I would have a condition that this thing is bigger than lambda minus, and that will give me like R smaller than lambda minus. So then this point on the real line will be lambda minus, and this point will be lambda plus. And in this case, if I modify here to kind of also have some real numbers lambda, so I will get a kind of interval from kind of lambda plus to lambda minus. Closed interval, and that would be my compactification of R using these positive half spaces. So now, in order to get like CP1 case, so this interval should contain a real line itself. So we need to kind of take this lambda. So take lambda plus minus. To minus plus infinity. So we want lambda plus to go to minus infinity and lambda minus to go to plus infinity. So we want to kind of add these points at infinity of real line. So yeah, so given, let me call it lambda a. So given this kind of lambda a and adjusting these values of lambda a to a certain infinity, we can get a quantification of Rn into kind of infinite polyton. Yeah, so and kind of another example which okay. Okay, so let me finish with just another example, and then we will next time we will kind of go over this compactification procedure one more time, but just kind of to give you example. So we can simplify R2 using kind of three lines at infinity. So here, like vector v1 would be 1, 0 vector, vector v2 would be 0, 1, and kind of vector v3 would be minus 1, minus 1. And then we can assign like some lambdas that go to infinity such that this object gives us kind of compactification of R2 to kind of infinite triangle. And then in this situation, kind of we need to be more careful in kind of specifying, like for a general point in this red region, on top of the general point, we have a two-dimensional torus. That is our interior point. We have two-dimensional torus, and then as we kind of approach boundaries, so boundary is kind of one-dimensional, so we should have a one-dimensional circle here, another one-dimensional circle here, and yet another one-dimensional circle here. To kind of glue all this thing into kind of smooth complex variety, we need a very specific homotopy types of the circles, and as we will see next time, but just kind of for completeness, so the homotopy types would be defined by this very same normal vectors b. So if you take this vectors b and kind of additionally ask that this vectors b they are just integer valued, so then by choosing homotopy types of circles to be exactly the same as this vectors b, all the construction will glue together into kind of toric variety, and the toric variety that we will get by this kind of simplification by a triangle will be two-dimensional projective space. However, I think for details we will talk about them next time. Yeah, so sorry for going over time. Yeah, sorry for being late and going over time. Yeah, I think we should definitely stop here. Because we are over 10 minutes over time. Yeah. So thank you. See you later.
Yes.
Here.
No. Yeah, but he did the thing he participated by Zoom, right? Give the address.
Unfortunately, I had a massive work.
Okay. Okay, I will finish early so that we could all go to the talks. Okay, so so we have basically finished. Ethan to finish the preliminaries on discussions on symmetric functions. So this is necessary before we move on to the version care of theory. Okay. So, but before really moving on, I think we still need one more key result. Okay, and so in order to talk about that, I do need some more preparation. Okay, so and this is the so-called Cauchy identity. Okay, so let me first write down the identity. So okay, so here right, so x1, x2, y1, y2. So just two sets of if you like just formal variables. Okay, yeah. Now, so the Cauchy identity gives an expression, an extension of this. Okay, and you just think of it as a formal power series. Okay, if you want to like expand it as a formal series in terms of the variables xi and yj. Now, clearly, well, at least formally, right, this expression is symmetric, right, with respect to any permutation, okay, of the set of variables xi, and also permutation of the set of variables yj, right? So therefore, you can already get, okay, when it ought to be expressible in terms of these symmetric functions that we have already studied. And in fact, the Cauchy identity is such as follows. So it could be expanded. Okay, so this is the identity. So here by S lambda x, of course, I mean the true function in terms of where the variables being the xi's, while S lambda y is the show function where the variable is the yj. Okay, lambda runs over all. Okay. Just as before, if you like, you can also have a truncated version. So namely, the identity for a finite set of variables. Okay, so the version we also have a version. For finite set of variables. Okay, x1 z and 1 and 1. Okay, then I will okay, right then you okay. Okay, this identity. Okay, and here, so now conditions ring, so just as before, and right, so it's this. So namely the length of lambda being less than 2. So there are actually quite a number of different ways to prove the Cauchy identity, yeah, okay, so we'll follow McDonald, so namely prove this using, so we prove this using the Jacobian identity that we have proved last time. Okay, yeah, there's certainly more than one way to prove this, okay, but let us give a combinatorial proof, okay, namely based on the Jacobi Trudy identity we have established last time. So we're using the Jacobi Trudy identity. Okay, so let us recall that so namely given any multi-index okay, right, so okay, yeah. So given any multi-index alpha, so A alpha, okay, so right, so this is and yeah, so we consider right. So in this context, the variables being x1 to x variables being so then we have this identity, right? So A x is equal to A delta x times this guy, right? So determinant of this matrix X H alpha, where recall. So where A alpha X is the determinant this matrix, right? X to the just let me yeah. So anyway, alpha I J J N. Yeah. Okay. All right. Okay. And of course, if you like, you can write it even more explicitly. So sum sigma right is element is symmetric group and letters sign of sigma and then okay, yeah, anyway, yeah, so yeah, anyway, so yeah, so this you have this open. So and delta is when alpha is delta. Okay, so therefore it's determinant of this this thing x j minus okay. So namely delta is the vector n minus 1 n minus 0. Okay, so and we know this is your depend on determinant. Okay, and finally, this H alpha is this matrix. Yeah. Alpha I minus F J. Okay. of course, I mean this is the uh, the complete homogeneous symmetric function, but respect only to the finite set of variables x1 dot up to xn. So if you like, you just set the variables with index larger than n, set those variables to be 0. Okay. Okay. Yeah. All right. Okay. So recall. So we have seen last time that from this identity we immediately get the Jacobi through the identity. So now let us apply this to prove the Cauchy identity, and we're going to prove it in this form. Okay. So right from this form. So this is so let me just remark. So it's easy to check. So this form this version implies this version implies when we have for infinite. Okay, so it's something we can check directly. So therefore, let us establish that this the version for finite set. Okay. All right. Okay. So, well, firstly, okay. So, firstly, for the text A, in 1 and n. So, if you look at this thing, okay. If you look at this thing, well, this is simply the generating function for the complete homogeneous symmetric function, right? With t being replaced by yj. Okay. Of course, when we define the complete homogeneous, the generating function for the complete homogeneous symmetric function is the product from I from 1 to infinity. But because here you just the number of variables being finite from 1 to n, so therefore it's just this. Okay, right. So therefore it is simply, this is just the generating function for the complete homogeneous symmetric function with finite set of variables and the formal variable t being set equal to yj. So therefore this is equal to, right, it's equal to this h h, okay, and then 1j to okay, r, yeah, r is equal to, okay, and hence this implies the following: when you take the product over j from, so you take the double product, right? Right, this is then equal to product j of this thing. So you just expand it. Right, so therefore this is equal to so here, so the notation is self-evident. So for alpha being say such a index. Then H alpha, Y alpha, Y to the alpha is of course Y1 to the alpha 1, sort of up to Yn alpha n, and similarly this H alpha. Okay, so H alpha, just product of these complete homogeneous symmetric functions with index being the alpha. Of course, the set of variables being X. Okay. All right, so now let us do the following trick. So now consider you multiply this expression with this Vandermonde determinant, namely A delta, with respect to the Y variables. Okay, so okay, so then of course this is right. This thing then it's equal to okay, right. So right, you so this is sum over alpha H. This guy is H over X A delta Y to the alpha. Okay, and then you just expand. Okay, this term. Okay, of course this thing is the Vandermonde determinant, but you can just simply write it out as in terms of the determinant. Okay, so this is sum over alpha multi-index and sigma in S n. Okay, so sigma H alpha X Y to the alpha plus sigma delta. Okay, yeah. So namely, so here I just go right because A delta Y is right. It is, as I say, it's really this Vandermonde determinant, right? So X K minus 9. And as I said, okay, this the delta exactly correspond to this vector n minus I, right? So if you like, you just expanded the usual expression for determinant, right? So it's really sorry, this should be okay, yeah, because it's the Y group. Okay, so the sign of sigma and then Y to the sigma of delta. Okay, where right? Y to the sigma of delta is just this yeah, you know, the variable y1 to the sigma of yeah, I mean yeah, anyway, you know what it is. Okay, yeah, because sigma delta sigma of the yeah, so the where with the ith and I coordinates or entry of sigma of delta being n minus sigma. Okay, right. So therefore this expression is exactly this one, right? So just the usual way to think about the yeah, determinant. Okay. So therefore plugging in right is equal to this. Okay, now so of course you can rewrite it in this form. So this is you write it as sum over beta in sigma in x sine sigma h of beta minus sigma delta x y to the beta. Right, you just make the you just make the substitution beta being equal to alpha plus sigma sigma then, right? Just make this substitution. Of course, so here again as I said, the usual interpretation. So namely that if one I mean this is an n tuples, right? I mean so n tuple index, as long as some of the one of the indexes is negative, then you interpret the whole term being zero. Okay, again the usual thing. Okay. Okay, so now we are ready to apply the Jacobi-Trudy identity. Okay, so remember this expression is this, right? So you multiply one Vandermonde determinant, okay, with the variable y. So let's multiply one more Vandermonde determinant, but with respect to the index x. Okay, so therefore a delta, but with respect to the variable x times a delta y times this expression. Okay, so this is then equal to okay this thing. Okay, so this thing, this expression multiplied with a delta x. Okay, so therefore it's this. Okay. But this is what, okay? But this is this is exactly a delta x times the determinant of this the matrix x beta that we had before, right? Oh, well, to be precise, okay, the variables respect to x for this. Right, we call that, so we call that beta, okay, so if you like respect the variable x, okay, so actually, so h beta is this matrix, right? H beta for any multi-index beta, okay, minus n beta I. So here beta is beta I minus n plus j. Okay, yeah. So I j. Okay, so therefore when you take the determinant, and of course it is exactly the corresponding to the delta, right? So therefore when you take the determinant, it's exactly this thing. It's exactly this thing. Okay, so namely h of beta minus sigma of delta. Okay. which is exactly this thing. Okay, yeah. Okay, so that's why I got this. Okay, and hence of course now we are now in a position to apply the Jacobi through the identity. Okay, so okay, so therefore this is equal to this is using the Jacobi through sum over a multi-index A delta x. Sorry, A beta x times 1. Yeah. Now in this sum, okay, remember this thing is equal to this. Okay. Okay. So now in this sum, okay, right, because recall once again that this A beta, right, is determined. Okay, so beta is a multi-index. Okay, so as before, so this term A beta is 0 is identically 0 as long as some of the indexes, any two of the indexes coincide. Okay, so or in other words, A beta is identically 0 unless the indexes beta are all distinct. Okay. Okay. So therefore, for any such beta, we have seen, well, essentially this is what we have seen when we construct the true functions, right? For any such beta, by permuting the indexes, you can arrange the index to be strictly decreasing. Okay, so or in other words, any such beta, namely the index bound all distinct, can all uniquely expressed in the following form. Equal to sigma of lambda plus delta. Okay. Delta of course is before. We need them to all time units. N minus 1 and 2 up to 0, and lambda is a partition of length less than or equal to k. Okay, so you can just identify it as n top. Okay, so it's a partition with length less than or equal to k. All right. Okay, so now we are essentially done because okay, anyway, so yeah, before moving on, okay, and A beta of x, okay, with beta being this thing, okay, so with beta being equal to sigma of this, so right, just as we learn in linear algebra concerning determinant, right? So when you interchange any two rows, okay, you differ by a -1 sign, right? So therefore, when you apply sigma, okay, to this n tuple lambda plus delta, so the effect is to, well, okay, so yeah, the effect is to multiply the sign of sigma on a of lambda plus x, okay. Well, okay, so therefore now you can complete the proof. Okay, so this is equal, right? y of beta n is a set. Okay, any such beta is of this form, so therefore the sum is now over lambda, so partition with length less than n, and then sum sigma of s n. Okay, and yeah, okay, so sine of sigma a of lambda delta. Okay, y of this sigma of lambda plus delta. Okay. Well, okay, but well, this is exactly the yeah, okay, just right. Okay, so this is the sum. Okay, well, this is exactly determined yeah, y to the alpha, right? This is sorry, I mean lambda pi plus a minus. Okay. So therefore, this is equal to sum over partitions lambda with length less than n, a lambda plus delta x plus a of lambda corresponding this way, a lambda plus delta y. Okay, so now you're done because you divide by these terms, right? Yeah, so you divide. Okay, right, but each of these is exactly the true form with respect to the variable x and y respectively. Okay. Okay, right. So this gives the proof. Okay, so what time? Okay, maybe a few more minutes. Okay, so let me give one more identity. Okay, because this will indeed be useful next time. So in fact, there's a kind of dual relationship between the Schur functions and the Newton power sums, right? So as I have already mentioned in previous lectures, so there are these very interesting number of identities between these different sets of bases for the symmetric functions, right? So we have already seen these, for instance, elementary symmetric functions, complete homogeneous symmetric functions, Newton power sums, and issue functions. Okay, so now in fact there's this close relation between the Newton functions and the Schur functions. So the identity relating these two sets of bases is actually the most crucial part of the theory, okay, in the representative theory of symmetric groups. But I will talk about that next time because yeah, need more time, but before that, it's good to establish the identity in the following form. So, okay, so the theory we also have the following. So okay, so this time instead of expressing in the basis of show function, we can express in terms of the Newton power sums. Okay, right. So here recall that indeed so recall. So that I've already defined these before these terms before, but just to recall the notation. So here recall this here for any partition lambda. So this Z lambda is defined to be the following. Okay, so where mi is equal to the number of times I occurs, number of times that I occurs in in lambda. Right. So let me so the number of times I occurs in the row coordinates, I mean the row coordinates. And as for P lambda, okay, so namely that if partition lambda is so the one, right, the row coordinates n lambda I everything equal to the length of lambda, then P lambda is defined by the product of these Newton power sums with index being given by these row coordinates. Okay. So we have more. This is much easier to prove. Much easier to prove. Anyway, so let's see how it's proved. So, okay. Right. Do you want to just leave it next time? You want to go to the talk? The build talk begin at 2:10. Maybe let's just go to the talk. Yeah, you're right. We don't. Yeah, let's leave it to next time. Okay. Yeah. 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 Oh, yes, certainly. Yeah.
So I'm not sure if I will be negative, but I will try to get the count. But if not, I mean,
Okay.
I think it depends on the consequence.
Certainly. Of course. Yeah. Okay, so let's then go to the talk.
То есть я как бы не могу какой-то нормальный фидбэк дать. Еще раз. Окей.